Very good afternoon to all, and I heartedly welcome Professor M.K. Datta for giving us his time and coming for an expert talk at such a short call. As far as a brief introduction of Professor Datta is concerned, he's currently working as the director for Center for Advanced Studies, which is an autonomous research-driven institution of the UP government, and it is an in-campus institution of APJ Abdul Kalam Technical University. And his main area of research is artificial intelligence, signal processing, computer vision. And in this very area, he has guided number of PhD scholars. And he has published more than 300 research papers in Scopus of the art work. Just it was the Dainik Jagran newspaper, and his work has been recognized on the national.
I think there is some network issue at Dean sir's end.
Yes, we cannot hear.
Taking this time, and over to you. We would now listen to you and your thoughts on this.
There is some voice breakage. Can you hear me? Is there some network issue? Hello? Am I audible?
There is some kind of echo coming at the background.
Datta sir?
Yes, am I audible?
Yeah, you're audible, sir. You please take over from here. We would like to listen about your research on artificial intelligence has an impact on disruptive innovations. Kindly take over from here.
Okay, so thank you. Okay, thank you. Good afternoon to all of you. I hope my voice is audible to all of you. I'll share the screen.
Yes, yes.
Okay, I'll share the screen. Just a moment. Give me a moment. Okay. Okay. I'll share the screen. Okay, here we go. Okay. Okay, so is the screen visible to all of you?
Yes, yes.
Okay, thank you. So good morning, good afternoon to all of you. First of all, thank you all for inviting me for this talk. The Dean of the Computer Science, Professor Munish, and the entire department and the university, thank you so much for thinking of me and inviting me for this talk. This talk I have kept more of applications of artificial intelligence, which we have worked in the recent past. This is, I will not discuss the basic architectures and computing part of it, like, gradient descent algorithms and, all regularization methods, etc. So, but this talk is mainly with some applications and some innovations that we have done using artificial intelligence. I wish that the examples and the work that I'll discuss will give you some kind of an idea what are the areas in which you work. So I'll keep my presentation like this: 5 minutes or 7 minutes. I'll talk about a little bit about challenges and introduction to artificial intelligence, and then I'll go ahead with some of the works which might give you some, thought-provoking and interesting ideas how you can also solve problems using artificial intelligence. Once again, I thank all the people of Galgoria University for inviting me for this talk. Thank you. Now, you see, the future of the entire technology, or you can say all science, all engineering, all technology, all parts of our life, somewhere or other, will be impacted, or will have an effect of artificial intelligence in coming soon. For example, I tell you, not long from now, maybe 5 years from now or 10 years from now, you go to a hospital, and before you see a doctor, you have to see a computer. You feed your data in a computer, and the computer will guide you with some kind of, pre diagnostic things, and maybe refer you to a doctor and refer you a test or something like that. And this is the future that is going to happen. So artificial intelligence is not restricted to computer science at all. The diversity and the acceptability of artificial intelligence across the community in different sciences, humanities, management, everywhere you see, has found a great impact. So this slide gives you an overview. It'll talk about object recognition, or you talk about medical informatics, or talk about biomedical devices, some ambitious projects like self-driving cars. I know many of you have heard in MIT in United States, which is funded by NVIDIA. The cars are driven at a speed of 60 miles per hour, 80 miles per hour. You can imagine how much computing is required if you want to go for a self-navigation, a self-driving car. Have you ever thought how much computing is taking place? Let's say we are driving our motorcycle or our car at a speed of 60 miles per hour or 80 miles per hour. Just imagine what kind of actuation we are doing. There's an obstacle, an animal comes in front of our car. We know we have to press the clutch and the gear and the brakes, and how much time are we left with? Just imagine. And if you want to replicate this with a computer, if you want to replicate a self-driving car with a computer, just imagine what kind of computing speed you are expecting. Let's say a car is traveling at 80 miles per hour. There's a sharp turn, or there's an obstacle, or an animal just coming in the way of the car. So how much speed, with what kind of speed you have to go for the object detection and respond? The car has to respond with the actuations like gear controls, and so what I'm trying to only explain you over here is that the power, the dexterity, the what I can say, the impact of artificial intelligence is absolutely open-ended, and there is amazing opportunity for the futuristic technologies to grab this opportunity to use. For example, we talk this slide shows a blind assistive device, or a document analyzer, or a medical imaging, or a pattern recognition, or a recommendation system. Like all of you, when you do a online shopping from an Amazon, you must have seen so many advertisements pops up of which is similar to your the online purchase that you've made. And all these things are made by all these things are some or other kind of artificial intelligence algorithm. So this slide, I take a moment, maybe a couple of minutes, to tell you that it is not only for the computer scientists, also for other branches of engineering, science, management, that AI is a powerful, impactful tool, which is definitely going to intervene in our regular life. A little bit about our lab. This is Center for Advanced Studies. We have a very high computing lab. We have a 5 petaflop computing speed. We have DGX2 servers. Maybe we are one of the maybe top 5. We are in the top 5 AI labs in the country in the education system. And at least I can tell you that computing resources is no longer a limitation in our lab. And of course, we are open to collaborate with your university and other universities also, where we can share these resources into some agreement basis. And these are the best supercomputers available. And also a little bit about the work. We have a specialized AI MTech program, machine learning MTech program, and we have some 5 to 6 PhD students working on AI. Also, we have 2 funded projects which are AI based. Now let's come to a little bit about the introduction of artificial intelligence. Maybe 5 minutes I'll talk. Now, what is this AI? If you really talk about the deep learning models, This is inspired, whatever algorithm computer scientists develop. Let me tell you, the natural algorithms are much more optimized, much more systematic, much more organized, much more, much more management of complex things. So human brain, if you really see, the human brain is is a fine computer. And let's talk about the human eyes. They're a fine visionary sensor. So if you look at how the deep learning model works, is inspired from the human, you can say, the sensory system and the human brain where the computation takes place. If you really understand, for example, you can see how with the biological neural network and the artificial neural network, we're trying to make some analogies. But then, for example, let me tell you a simple example. Okay, if I bring a cat or a dog, in front of you and I ask you, what is this animal? You'll immediately tell this is a cat, or you'll tell this is a dog, right? Why? Did you ever did you ever realize that if I bring an animal which you have never seen, some very something, an animal from Africa or somewhere, I bring and I show you which you have never seen in your life, you can't tell what is this animal. It's not that the sensory organs are not firing, the neurons are fired. The image of that animal is formed in your retina, and the sensory organs, the neurons has already been fired. But what happens, as the neurons are fired and it reaches the visual cortex, I tell you that in the visual cortex, it cannot make a correlation and a probabilistic interpretation of what can this be. So learning and pumping. So for example, let's say you students are 20-year-old students, or let's say I'm a 40-year-old professor, and I have with me 40 years of experience where I have been trained, and I'm learning things. For example, I look into a dog from the right, from the left, from the top, from the bottom, from the from the I can see the tail of a dog, or I can see the face of a dog or the ear of a dog, and still I can say this is a dog. I'm backed up with 40 years of experience. For you students, you are backed with some maybe 20 years of experience where you have been trained. Now you expect a computer to become that much of intelligence. Let's say you want to pump in the training that I had got in my last 40 years of my life. You want to pump in that much of information in the computer within 1 hour or 2 hour, and just imagine how much computing speed you need for that and how much information you're going to pump in. Okay, so this is all about artificial intelligence, the computing speed, and the amount of information needed to train a model. Now, the difference between artificial intelligence is definitely the larger umbrella, and machine learning is a part of it, of course, a major part of it, where techniques like support vector machines, where you do the distance measurement, similarity indexes, and you take decisions on some kind of supervised learning, where you extract features and you work on that. And deep learning goes one step ahead, and deep learning is you can say is an advanced form of machine learning where the manual feature extraction is completely remote and it's completely automatic, and at different layers, at a different scales, the information is fed to the model to train it. And of course, deep learning is very popular in the current scenario, maybe from 2010 2012. It has really become very popular. If I ask you the difference, you can see machine learning is what machine learning, there will be an operator, there will be a human intervention. Right, there will be a one AI scientist or an AI operator who is going to do the manual feature extraction or handcrafted feature extraction, and then you pass on that information or train the classifier models like super vector machines or naive Bayes or random forest, or there are so many supervised ensemble methods, and you train your model to understand and learn. The training is complete through the handcrafted features. Now you go one step ahead in deep learning and you remove the manual extraction method. It becomes completely automatic, right? It becomes completely automatic. And here is the power, the innovation, the impact of deep learning, that because sometimes what happens as a manual feature extraction, we sometimes we do not know, are we really picking the correct features which are discriminatory in nature to train the classifier to the maximum possible extent, right? And these kind of probabilities are eliminated in deep learning, where a sequence of hidden layers comes into picture, and there's a sequential training of the data, and the information passes through a sequence of layers, and you can be more assured that nothing will be, if there is anything which is discriminatory in nature, will definitely be trained to the model. And here is the innovation and the impact of deep learning over conventional machine learning. A little bit about the for example, if I ask you, you look into your face and you say this is a human face, Now, even if I show you a cropped portion of the face, if I show you the jawline or the eyes or the ear or the nose, still you will say this is a face, right? So did you ever imagine how? For example, if you train a computer, if for example, if you train a computer for a facial recognition, you need to understand that the computer will, check for the eyes and the nose and the jawlines and the lip contour and the triangulation formation of the eyes and the nose, and then take a decision. This is a face, right? Now, a human being, even if you show a crop, for example, if you push a cropped image of a face to a computer and ask if it is a, if it is a face, the computer with ordinary, I mean, with the normal supervised training will not be, in a good position to tell that. But if you look into the building up method of a deep learning model, or the way the human brains, for example, the sensory organs of our eyes, the neurons are fired, you know how it works. Let's say we start from the low level features. The low level features are the dots and the lines and the edges and the boundaries, okay? And you build up on that, and you start building up to the mid level features, like the eyes and the nose and the ears and the jawlines and the lip contours. These are the mid level features, and then on the mid level features, if you build up in a large scale the high level features where the actual facial interpretation comes, maybe the combination of the eyes and the nose and the lips, and then you build up. So and this is how the human sensory organs work. Now, if you really understand, an experienced person, even if you're looking at a cropped face, he will still say this is a face. A computer unfortunately cannot do it with normal, supervised and feature extracted based learning. But can we do it with the help of deep learning or not is the important question. And yes, I may tell you, there is enough probability. If you really understand the model, how it works, you will see the deep learning model works, starts from the low level features and starts building up with the mid level features and goes to the high level features. Now, a question comes into our mind. For example, in the current times, you see that the deep learning models are very popular, and deep learning models is built upon, mainly you can say, the backpropagation algorithm, right? The CNN works on the convolution neural networks or the RNN model. They basically work on backpropagation algorithm, and backpropagation algorithm is nothing but it's elementary calculus. Okay, it's derivative, it's partial derivatives in which you link up the input and the output through a sequence of partial chain derivative, the chain differential rule. Now my question is, 1960, 1952, the stochastic gradient model was presented, and 1974 the backprop comes into picture, and 1986 you already have a multi-layer perceptron model, and 1998 you had the CNN model. But what was that the insurgence of the deep learning models comes all of a sudden in 2012, 13, 14. I think all of you know, maybe the young kids, I don't know how much if you're studying, you must be knowing, the deep learning models have become popular only after 2010. Maybe 12, 13, 14, 2012, 2013, 2014, 15 was the surge, and currently we are really into a boom. Now, there are basically a few reasons. Come to the next slide. Maybe. Now, why the question is why deep learning is so popular now, and how deep learning has taken over the existing technologies so much. So neural network, I mentioned 1956, the gradient descent algorithm was there, and backprop was in 1974, right? There are three important reasons if you really understand. Number one, to train your data, as I was mentioning, let's say I'm a 40-year-old professor, and for the last 40 years, information are fed into my brain. I've been seeing dogs and cats, and I've been hearing sounds, and I'm interpreting. Now, if you want to train a convolutional model, let's say if you want to train a deep learning network, you need a huge amount of data, because these networks are data hungry. The more amount of data you feed into this network, the more intelligent and more accurate and more optimized they become. So one important reason for the resurgence of the deep learning models is the availability of huge server space. Today, I think all of you appreciate that 10 years back, or maybe 15 years back, we were having MBs of mobile. Our mobile phone will have a card, and it'll have 1 MB or 5 MB or 10 MB data, right? Today we are carrying hundreds of GBs and thousands of GBs in our mobile phones, and the servers and the subs and the workstations has got TBs of data, 10 to the 12 bytes of data. So the access to data and the storage of data is no longer a challenge. And since the CNN models are so much hungry for data and data driven, so that is something that has really pushed up. The second thing is the hardware. Now, if you see, companies like NVIDIA have come up with technologies like CUDA, CUDA. You know what is CUDA? computer unified diversified architecture, CUDA. And these CUDA technologies have gone for a massively parallelization of resources. And maybe if you go 15 years or 20 years back, if you see the GPUs, the execution of an image, any image model training will depend sequentially. So you have to wait. If you put maybe 1,000 images for the model to train 10 years back, it'll take 24 hours, maybe 48 hours, because the GPUs will be occupied. Today, the same task with the amount of speed that we have, we can do it in 10 minutes, 5 minutes. So that amount of massive parallelization of the resources have come up, and also the big players like the Microsoft or Google, they have given you architecture. For example, the TensorFlow sequential model is one of the most popular model. I think you students are more, in India normally, because TensorFlow sequential model is an open source model. So it has got a wide acceptance, and I'm sure you guys, the students who are into AI, you are using this TensorFlow sequential model. So the availability of the architecture, for example, if you want to do a hidden layer architecture, if you want to build up a hidden layer with let's say 50 layers, and you want to optimize it using the gating functions like the activation functions, and you want to check the regularization parameters, you no longer need to write those 100-line codes or the 1,000-line codes. You already have inbuilt libraries. So the improved techniques and the models that, of course, Microsoft have given you the CNTK model. The PyTorch model is also very popular. And of course, the Google, that the TensorFlow sequential model of Google is absolutely popular. And even I use TensorFlow sequential model because it's an open source, and they're not charging. Now the question is, with the amount of with the resurgence of this, the big data and the improved parallel hardwares and the architectures provided by the big companies, massive computing speed we have gained. So if you see the third image from the top, you can see some bounding boxes, the yellow ones and the red ones. Just imagine, I'll tell you an example. For example, let's say you have a video. A video is normally 30 frames per second. I think all of you know, normally a video will be 24 to 30 frames per second. Now 30 frames per second, what does it mean? One frame is 1/30th of a second. So just imagine how much time you're left with. Now, if you want that every frame to undergo a deep learning model, and you are going for an object identification, just imagine what should be the power and the computing speed of that. Now, if you look into, there's a model called YOLO, Y-O-L-O. I guess many of you who are developing architectures, etc., you must be knowing. YOLO is a very popular architecture. This picture is taken from YOLO. So let's say even and YOLO can process 1/30th of a second of a video frame and identify with multiple bounding boxes all the different objects available in that frame. Just imagine the power of computing that we have reached. Okay, and on the second image from the lab, the second image from the top is the NVIDIA project in MIT. They're going for a self-driving car, and I think if you in Google and find out, maybe 80 miles per hour the self-driving car can travel in full traffic, right? So just imagine what kind of computing speed we are reaching and what kind of training we are doing. And I have put all the slides for you to show you the power of AI, so that you get motivated, and maybe you can take up as a professional AI scientist. Manual feature extraction. Now, for example, if I ask you, you do the feature extraction of a dog. Now, what you'll do, you'll say dog has two eyes, the dog has two, this geometrical feature, and the eyes and the nose and the ears, and you'll give a geometrical contour, and you'll give some, some features, some this. And, let's say I talk about a medical imaging problem. Let's say you want to find out, the presence of a tumor in a brain MRI. Now, you must have domain knowledge. Okay, you should know how does a tumor look like? What is the geometrical interpretation of a tumor? In textual analysis, how does it look like? In spatial analysis, how does it look like? And also then you have to specify the features, that the tumor may be circular in shape, or it may be an elliptical shape, or it may be an elongated structure, and also detect the features for classification. So please understand what I'm trying to emphasize. Previously, before 2010, where even somebody like me, for example, I was into machine learning, supervised learning till 2012, 13, 14. Even I have papers in 2014 and 15 with supervised learning. Of course, after 15, I do not use it. No, the issue is, the domain knowledge, the feature specification, and also, we do not know whether we have picked the rightest combination of features in training the classifier. We don't know. And of course, so doing so, we may not end up with training the proper and the best model, and hence the challenge and of an underfitting or or a non-convergence of the test and the training curves where there may be a divergence at some point. These features you cannot eradicate. Now what happens if you bring in DL? Let's come back to the next slide. Now, also the issues, if you see, there's something called as an occlusion. Now look into the second feature, occlusion. In occlusion, it becomes hard for the image processing or the computer vision engineers to extract the features accordingly. Now look into the cluttered background. Now there is an animal and there are leaves, and if you really see the appearance of the animal is pretty similar to the appearance of the leaves. Now how do we extract feature? Don't you think this is a challenge? The intra-class diversity. I ask you, give me the features for the toys of some cars. Somebody is yellow, some fellow is blue and red and different structures and in different shapes. So how do you go for the features? Is it really possible for manual feature extraction? There may be intra-class diversity is a huge challenge. I tell you, if you work with medical images like X-ray or MRIs or ultrasounds, you will see that intra-class diversity is a huge challenge. And then if you want to do for handcrafted or manual feature engineering for the inter-class diversity, you will definitely there's always a chance we end up with the selection of non-optimal features. That problem always remains. The deformation of the objects, you can see if you use geometrical features to represent a coffee mug, if it is deformed, the computer may not be in a position to do that. The scale variation, the scaling, the illumination intensity, the viewing angles, the orientations, the deformity. Let's say there's a blurring problem, the last one. So if it's a blurring problem, but what I'm trying to explain here is that as a human vision, please understand, as a human vision, please understand one important thing, always remember, the human eyes and the human brain are the best combination of the vision sensors and the vision computers. Any computer, any sensor, any camera or any processing speed cannot be that. So with human intelligence, we can actually overcome like clutter background, the interclass diversity and others, but then using a computer and training them with handcrafted features may always be a challenge. So here is the power of deep learning, where you do the training of the model into different scales. Maybe a few more slides. Now this is the building up. How do you build up the features? Let's say you wanted to go for a facial recognition, the eyes and the hair color and the facial structure and the jaw lines and the lip contours. For example, a car. You go to the lower features, the license plate or the doors and the windows and the headlights. So you build up from a low-level features and start going to the mid-level features and going up maybe similarly for training to find an object like a house. You have a window pane and a door and so many other features. So the same story as I mentioned, from the low-level features to start building up the mid-level features and go and then you go for the low-level features also. But this is a video. If you see, this is how a convolution. This is an animated video. You may like this video actually. So you see, this is how it has been spread up into different sequence of things. The digitization has been done, and then it is passed through the different networks of layers. The activation functions comes into picture to remove the non-discriminatory information and keep the discriminatory features at the last point. This is a softmax function with a certain amount of probability. It will tell you the probability, or it will tell you whether this correct detection of the object or not. So this is just an animated one. So once again, you can see this is a basic structure, inputs, and how the hidden layers are. This you study in your classroom. I will not, maybe you can see the max pool layers comes into picture, downsampling operations, and how do you reduce and go ahead. It's step by step in different scales have been represented. The convolution operation, you can see a filtering operation taking place and the convolved nature. It's I think the students who are studying that this is a basic convolution operation. It is the element-wise multiplication and then summation of the filtered window and how it is coming on the right hand side top. You can see the features operation is taking place, and then you go for the downsampling operation using max pool, etc., for making the features. So this is the representation. Okay, so this was a very a brief overview of CNN. Mainly, I was talking about the challenges. I was talking about the interpretations and what are the probabilities of opportunities there are. Now, from here onwards, I'll come to some machine learning and deep learning applications in which we have solved some problems. I think I have got 1 hour time, so maybe some of the time is consumed. Now, these are some applications. From now onwards, please understand, this is not a deep learning lecture, so I'll keep it to some applications where some interesting problems were solved. This is a problem. I don't know if you know, there is a disease called osteoporosis. Okay, osteoporosis is a deformation of the bones. Uh, at different at older ages, it's very much prevalent with the woman. Maybe after 50, 55, or 60, you'll see maybe a huge percentage of the people in India and of course across the world also, they're affected by the bone density problem. The bone density goes low and they find difficult in standing, walking, etc., etc. So the question is, to diagnose the osteoporosis, you need a machine. You need a very costly machine called as dual energy X-ray absorptiometry. We call it as DXA. It's a costly machine. Now, for example, if you're in Lucknow or in Delhi or in Noida, in big cities, these kind of machines are available. But India is a country of villages. We have remote places and villages where these kind of machines are not available. So what is the alternate solution? Okay, start thinking. The innovation thing starts from here. I think 2015, when I was traveling to Europe, I met these two guys. Rachid is a computer scientist like me, and Eric is a doctor in the Hospital of Orleans. It is in France. You can take a snapshot of this slide because I've mentioned the published paper. If any one of you find it interesting, you can download the paper. You can read for yourself. Okay, the paper was published in Computation Biology and Medicine. So I'll tell you what is the problem. The problem is, can we diagnose osteoporosis from a normal device like X-rays? Okay, because DXA in a country like India, it is very difficult to get access to something like it. Now, X-ray is pretty cheap. Even small villages and small cities, small towns, you will have an X-ray and you can do an X-ray with maybe 100 rupees or 200 rupees. Or X-ray is pretty cheap. Now, can I run a software on an X-ray to estimate the bone density? Can I do it? And then I return that whether this has got symptoms of osteoporosis or not. Initially, when we started the discussion in 2015, the paper was published in 2017, I think. In 2015, when we started, when I met these two guys in Europe, so we started discussing, can we do it? And and if you go and ask any radiologist, you go to and ask any X-ray doctor that is radiologist and ask them, okay, can you find the bone density from a normal X-ray? His answer will be no, absolutely no, you just cannot. X-rays are mainly to identify fractures, etc. I think all of you know a deformation of a bone or a breakage in a bone or some fractures, etc. You can very easily identify from an X-ray. But identification of bone density from X-ray is a really challenging task, and initially it seemed like it was not possible. So we started thinking, can we do it? Can we do it? Okay, I'll skip some of this slide because pressure of time. What we did is that we, of course, the data. I need to acknowledge these two guys because Eric was the doctor who collected the database from the Hospital of Orleans, and Eric and Rachid both are co-authors in this paper. You can see Anushika is a student of mine, and I'm the one. And now we collected the data from France. Okay, you can read more about. Now we did a very systematic pre-processing. Okay, we did a very systematic pre-processing. You can read more about it. So because in a normal visualization, it was not at all evident. After doing the pre-processing, you can see we have done some some intensity adjustments and some contrast adjustments also. You can read more about it in the paper. And then if you look into this slide, look into the table at the left-hand side, the bottom table, two values are mentioned for the principal component analysis. I think all of you know principal component analysis, right? So the first principal component analysis and in the first principal component and the second principal component, we could find two features. One was your contrast, and the other one was your that was your standard deviation. You can see two statistical features were showing good amount of discriminatory deviation. So what I'm trying to mention, a radiologist will only look into the spatial representation of the image. It may be very hard for the radiologist to look into the spatial representation of the image and give a decision about the bone density. But the same thing as a computer scientist, if you can do a mathematical transformation of the image into a different domain, maybe you end up finding some discriminatory features which may be very efficient in training a classifier. So what do? So this contrast in first principal component and maybe the standard deviation, the statistical parameter in the second principal component were highly discriminatory in nature. Then we trained 4 AI classifiers, 4 machine learning classifiers. This paper was written in 2016. So those days machine learning was quite popular. So support vector machine, we use name-based, we use KNN algorithms, and we use also artificial neural networks algorithms. But all four were supervised, and you can see we got some very good accuracy of around more than 90% in the which was reported in the paper. There's a scatter plot curve. You can see how the testing, the training models was done, and of course, what I'm trying to emphasize here is that this is a problem. This is a problem. Osteoporosis is a problem, and in a country like India, we do not have access to very costly machines. So, is there a solution to that? Can we innovate? So, this is an innovation, of course. Now, this is into a clinical in France because the database belongs to these guys. In France, it is already under clinical trial, and once the clinical trial is, because the COVID situation has a little bit different. Once the clinical trials are complete, and if you get a okay from the regulatory body, these softwares can be installed. Let's say this, and I can give it to you for free. Just install this software in any small B grade, C grade cities, and just take an X-ray, insert the digital X-ray into the thing, and just it will return you whether you have what is the nature of the bone density, and tell you whether also osteoporosis. So, and if you really understand, if you in a country like India, you'll appreciate in a country like India, we definitely need these kind of solutions, and maybe very strategic feature extraction from the images, and strategic machine learning algorithms can solve and bring in this kind of innovations. I've already shown you the paper is already published. The paper is attracting a lot of citations. You can download the paper and you can read for yourself if you find it more interesting. And there is more scope to work in this paper, which is mentioned in the paper itself. Well, this is another work which I'll explain. I'll talk a little bit about it. Just checking, am I audible to all of you? I mean, am I audible? Slides are okay?
Yes, sir.
Yes, sir.
Okay, great. Thank you. So, this is something, if you remember in last year, or maybe in the month of May to 2020, you do remember, I think all of you remember, the migrant laborers were returning from their, workplaces to, places like Uttar Pradesh. And at that time, there was a shortage of in the RT-PCR and the COVID testing things, right? And there was a lot of problems. I don't know how many of you know that in the highways, that the highway of that Agra Lucknow highway and other national highways, people were traveling on their own, and they were trying to go back to. No, here comes a problem, because RT-PCR is kits are limited, and it also takes a lot of time for getting. And those times, if you remember, maybe in May 2020, nobody had very much clue about COVID. A lot of things were coming up. So can we, as a scientist, as a computer scientist, can we give a solution to that? We started working. Me is the white shirt guy, right to our Honorable Chief Minister. And if you see the blue shirt guy is our Vice Chancellor, Honorable Vice Chancellor Professor Pathak. And on the left-hand side, the cream color shirt, he is the Vice Chancellor of King George Medical University, which is one of the topmost university in Uttar Pradesh. It's in Lucknow. And that red turban guy is a doctor. He's a pulmonary doctor. He's a very popular doctor, Harpreet. And Rakesh is in the right-hand side of our Honorable Chief Minister. He's a PhD student who works with me. So we've started working. What we started doing is that we collaborated with King George Medical University. We collaborated with a medical university in Saifa Etawah, and also one government medical college in Rajasthan. We started collecting the information. We started collecting the information of chest X-rays. Now, okay, this is, you can, if you're interested, you can take a screenshot of this. The paper is already published in an Elsevier journal. This is a good journal, 3.5 impact factor journal. You can read more about the technology. I'll just brief you what we started doing here is that. So, and this technology was developed mostly, for that migrant laborers who were returning. And we used this with a great amount of success. We installed a van, we took a van, a small mini truck kind of a thing. There was an X-ray that was installed, and a computer operator was there where the X-ray will be subjected to this, and we gave decisions. And we are having more than, I think, maybe 90% or 95% accuracy. The paper is also published, so it was a user-friendly thing. There was no need of trained manpower for using this. It was standalone. You don't need an internet connection. Single click, you do a lot of things. It was very fast, in terms of computation, in terms of your. Now, what did we do here is that. Now, I'll tell you about the challenge. COVID-19 and healthy is very easy, actually. COVID-19 and healthy, discrimination is quite easy. If you train it with any pre-trained model, also it works. But the problem comes if there's a guy with a viral pneumonia and bacterial pneumonia. See, bacterial pneumonia, viral pneumonia, and COVID-19 has got some kind of similar chest conditions. So here is the main challenge. So now, if you want to do a deep learning model with healthy and COVID-19, that should not be a problem. You'll definitely get if you've got a good amount of database, because currently in NIH and if you see GitHubs and Kaggles, etc., a lot of people have posted the database. You can work on that and you can see. But still, if you see, that bacterial pneumonia, viral pneumonia, and COVID-19 quite similar in nature, because all these three are chest conditions. Now, we started making a model from the scratch. Okay, you can see collection of images, segregation of the unwanted images that maybe if there is a noise or a clutter, then documentation part, then notation part, the image data set with the notation, and then dividing it into training, validation, and testing, and then give it to the doctor for that. Now, this is the pictorial representation. The architecture was made. Next slide. You have the architecture. If you are interested in our architecture, take a snapshot of this. I've given you the filter dimensions and the architecture details. The windowing operations are mentioned over here. If you are interested, also read the paper. And interestingly, this architecture which we built, the filter sizes, etc., all mentioned. You can take a snapshot if you're interested. Also, the hyperparameters we have given, and these were the most optimized hyperparameter combination and the filter specifications, on the basis of which we made this network, and it was a run against time. If you remember, we were working day and night. I'm very proud of my PhD student Rakesh, was working almost 24, maybe 20 hours a day in putting the things, and he was sleeping in the lab. And we trained them, and we got very good accuracy. More importantly, more importantly, this paper is, of course, the paper is a mark of your, it remains as a digital object, as a credit of your work. But more importantly, this software, this COVID detection app, was used by the KGMU people in a massive scale for screening, mostly for the laborers who were returning to their original villages. So a timely intervention of artificial intelligence technology, into a societal problem definitely can make a difference. Also, my responsibility to thank the people. You can see there are many doctors associated, mainly the doctors from KGMU and that Government College of Kota and Government College of Sci-Fi. So acknowledging these guys, because they were also the co-authors of the paper, as well as they took a lot of pain in providing us the data, and we were training it. That time in May 2020, we were not having these DGX2 servers, so I had to collaborate with the European guys to get access of their GPUs. So hence this guy Radim and Cesar and Carlos, the three scientists from Europe who are also the co-authors of this paper. We got the GPU access from their labs, and we started collaborating in developing that architecture. Now, this is another project. The cardiovascular diseases, as you know, is a major problem. Many people die across the world because of CVDs. So is there a solution? For example, if you talk about a country like India, for example, if you say somebody is living in the primary, villages and maybe remote parts of the country, the primary healthcare centers are really not very much equipped in our country to, make proper diagnosis of cardiac diseases. So is there a solution for this? Okay. So of course, before I go ahead with that, I need to acknowledge and thank the Department of Science and Technology, because this entire work is supported from the funds we have from Department of Science and Technology. This is an ongoing running project that we have. Also, my responsibility to thank the guys who worked. Dr. Vivek Nangia is a very popular doctor in Fortis Hospital in Vasant Kunj in New Delhi. He's the head of the pulmonary section. He was the lead principal medical scientist in this. And of course, we have some other guys who worked with that. Carlos and Radim, because these guys had helped me in training the models. I used their GPUs, and of course, they were also helped me in developing the architecture system. And others are my students who worked with me in this project. Now, what is this? Okay, and this is so. Can we have an automatic machine which will tell you a little bit about the condition of your heart and the lungs? Okay, so this is the proposed device, and can we use an artificial architecture model or some technology? Can we do it? Okay, so what is the proposed device? Okay. You take a maybe a sensor, maybe a stethoscope, record the heart sound, the cardiac sound, process the heart sound using some artificial intelligence, some computing method, something, and are we in a position to make a decision if the heart sound is normal or the heart sound appears to be abnormal? And if it appears to be abnormal, can we actually classify it in terms of some disease? For example, mitral regurgitation or ventricular fibrillation. There are some cardiac disease or which commonly occurs and leads to heart arrest, the chest arrest. Okay, so can we do this? Was the question, and can we make a device, right? So this is the the device that we have. I'll tell you more about it. This is a screenshot that you can see. Okay, this is a small device. I'll show you more about the device. This is the screen. Just enter the patient name, the age, and the gender. And of course, this device is a 3-in-1 device. You can use it for cardiac, you can use it for pulmonary, and you can also use it for prenatal. I'll tell you about all these three. I'm currently talking about the cardiac. The cardiac signal will be displayed. Then click the option, record signal, open a file and start test, and it will generate you a report. And the report will look something like this. Okay, whatever name, etc. you put in this, you will see the name, etc. have been displayed in the report. And there are some features. There are some parameters like the some mean and some statistical features, etc. And these features, we know this is the diagnosed value, and we also know the value of how the value will be there for a normal person, and if it is diagnosed with an abnormality. So here you can see this is the report. It says the results of the heart sound under the test are follows. The heartbeat appears to be mitral stenosis. So mitral stenosis is a cardiac disorder. So please understand, this is a small GUI which can be used by any person in a primary healthcare center. Okay, maybe anyone, just somebody who can use a mobile phone can use this. Is click, 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 click. There's nothing doing. Just record this. I'll tell you more about it. And this is how the report is generated. And we can SMS this report or WhatsApp this report or print this report and give it to. So this can work as a primary screening device, at least in remote places of the country. Now, how does it work? Just if this is an animated picture, you can see this. So give you some kind of an idea. Okay. Now this is what it is. Is an animated picture. Can you see an animated picture in your screens? Can you see, all of you? Can I ask you?
Yes, sir.
Can you see?
Yes, sir.
Okay. Now, see, this is the patient. The patient comes, you take a stethoscope. This is an electronic, if that stethoscope is connected with a microphone, you record the signal. The signal is, collected through a computer. It can be a mobile phone, it can be a single board computer. And then you do some amplification and filtering. It gets transformed into a digital format. And then you're pushing it to a deep neural network. In the deep neural network, we already trained it for identification of the devices. Then I've shown you the GUI, the graphical user interface of the device. Okay, and this is the device. You can see. Click this device. A report is generated. The report is given to the, and then the report is given to the patient. It's a completely automatic process, And what you can do is that if you can, I'll tell you more about the architecture of this device. So if you really see, this device is interesting in its own way because it's a standalone device, and at least it can work as a monitoring system in primary healthcare centers, in villages where there is shortage of cardiac, heart specialist doctors, cardiac monitoring systems. So this is a device which can work. And how this device works, we'll go ahead with it. Now, please understand, the heart of this device is in the center. You can say, I call it as an intelligence stethoscope. This is the device which we have completely made in our lab. I'll show you about the designs, etc. The heart of the device is a deep learning model, okay, which we have trained. The deep learning model, which we have trained using the signals collected from various hospitals. I'll tell you more about it now. Now, this is what it is. Just give me a moment. Just a moment. Okay. Now, this is the little bit about the places from where the samples were collected. You can see we have collected data from the Fortis Hospital in New Delhi. We also have collected data from King George Medical University in Lucknow. We need to acknowledge and thank them. We also had collected a database, a public database from PhysioBank, that is a standard public database available online for the research purpose. Okay, and the problem that we had considered here, if you really understand the problems that we have considered here, was a multi-classification of cardiac disorders. Now, if you really know about the cardiac disorders, some of the most commonly occurring cardiac disorders are like aortic stenosis cardiac, mitral regurgitation cardiac, mitral stenosis cardiac, mitral valve prolapse, and also we considered a class called normal. So it was a five-label multi-class classification problem. Similarly, we also worked for this was for the cardiac, the heart sound. Also, we worked for the lung sounds also, and in the lung sound, we worked with capturing the sounds of the lung and trying to make a deep learning model. I'll show you I'll show you more about the details. I'll show you more about the details of this. Here in the lung sound, we considered different. Sorry. Here in the lung sound, we consider different categories of sound like cryptation. Then we also use normal, then raunchy, wheezing, cryptation and wheezing, raunchy and wheezing. Now these are the various classes of sound that are actually that on the basis of this sound you can make a diagnosis if the patient is suffering from bronchitis or maybe some other respiratory problem. So these are the sounds that were collected. Now this is the actual module that we have worked. Okay, so the recording of the PCG signal, how the recording of the PCG signal and how you are electronically recording and saving the signal. The signal processing. So I'll tell you a little bit more about it. The signal processing, the augmentation part. I think all of you know, in the people who are working with deep learning models or machine learning models, we go for data augmentation. Data augmentation in this particular case was time synchronization, time dilation, TSM effects, time synchronization, and also we added some noises to make the training model as robust as possible. Amplitude. Then we went for the amplitude normalization and the filtering part, because filtering is a very interesting tool over here, because if you know the frequency range of the cardiac signals, we can eliminate other body sounds, or even let's say there's a background sounds, etc. We can remove the clutters using a proper filtering method. The feature extraction, and then if you really see, we had made a one-dimensional CNN model, because two-dimensional CNN model is quite popular. I'm sure many of the students in this university is also working with two-dimensional CNN models, like for image, etc. One-dimensional CNN models are a little bit less popular, but the same story. Instead of going for a filter, like let's say in a two-dimensional CNN model, you take the filter size 3x3 and you do the winding operation and the convolution operation and the Maxwell operation. In one-dimensional CNN problems, what you do is that, because a one-dimensional signal is a straight line, right? Is a vector. So you'll take a simple n. Let's say if it's a n cross, if it's a 1 cross n is a signal size. So you take a small window, for example, let's say 1 cross p, and you move this p across the signal and repeat and do the same convolution process that you do in a two-dimensional signal. I'll show you more about it. So this is if you're interested about it, you can take a snapshot of this, because the filter size, the configuration, and also the hyperparameters that were used in this deep learning model I've mentioned. This is the first deep learning model that was reported with this database. The paper is published in Computers and Programs and Methods in Biomedicine. There's a very popular journal, 5.5 impact factor journal. I'll show you more about the slides also, about the publication also. So this is the architecture of the deep computing neural network architecture. And if you're interested, you can take a snapshot of the architecture, and if you want to replicate this work. But the results were very good. You can see more about this in the paper. We got more than 90% accuracy. Now this was for the lung sound. Now in the lung sound, what we did, the collection of the sound, of course, the labeling part, the signal augmentation, and also the pre-processing part for cleaning the clutters, etc. And then the same story. We did a one-dimensional CNN network. We did a one-dimensional CNN network. The paper is already published. I'll show you. I'll tell you about the paper also. This paper was published in Neural Computing and Applications. Neural Computing and Applications. The architecture is completely disclosed. There's nothing. It's completely public now. Now this was the architecture for the sound. You can, if you're, I think this is very small, but anyway, if you have interest in that, you can take a snapshot. You can see the filter size and the hyperparameters that we have used in developing this architecture. This architecture belongs to us, and the results, and we have shown it that competitive with other proposed results. A little bit about the, I don't think you are, if you're interested, this is how we made the stethoscope actually. We were connecting the diaphragm with a small microphone, and there were some design rules we considered so that we can capture the maximum of the heard sound without getting into more of clutter acquisition, etc. The mechanical design, I don't think you people will be interested on that. This is more about the mechanical design of the structure, and this is how the device comes up. Okay, the heart of the device is a deep neural network, but then to make the device standalone, you have to integrate it with a. We used I think an NVIDIA Jetson Nano, or I think you can use a Raspberry Pi also. Raspberry Pi is also a quite easy one. I think how much? I mean, Raspberry Pi will cost around 3,000 rupees. So the architecture model that you have trained in a server or in a good GPU, you can port it to a small single board computer like Raspberry Pi or a Jetson Nano. So these are the specifications of the device that we have. And if you really understand, take the stethoscope, connect it to the heart, record the signal for 10 seconds, enter the patient details, single click, a report will be generated telling you the condition of your heart and your lungs. So don't you think these are innovations using artificial intelligence in clinical healthcare sector? And for a country like India, if you really understand, for a country like India, you really appreciate that these kind of devices. We've already filed the patents. We have already, this is the structure of the block diagram of the paper, and this is a laboratory photograph of this. I think this is the final prototype developed. Okay, and this is the publication that have come up. You can take a snapshot of this slide, because here you can see where the papers are published. You can download the papers, and you can see more about the architectures and the hyperparameters if you're interested in replicating the work. We already have the patents of this device, and the clinical trials are getting a little difficult because of the COVID situation. If the clinical trials are perfectly fine, then we can definitely go for commercialization and put these devices using artificial intelligence and deep learning models for societal benefits. This is another problem. This is a similar problem. It was a part of the same DST funded project. I kept it separately. There was a newspaper article published 2 days back about this paper. This paper is already published. Now, what happens, when a pregnant lady, when there is a child, there's a what do you call it, the fetus. The fetus, if it is deprived from some oxygen, maybe it may occur for different postures, etc., and maybe some different postures, that if the fetus is deprived of adequate oxygen, a situation called as hypoxia that arises, and the disorder is called as fetal acidosis. Now, fetal acidosis is a severe thing, and this may actually lead to other complications of the pregnancy. So now, how do you do that? So we started working with a deep learning model. Okay, I'll tell you more about it. The paper is published. You can see this paper is published in Biomedical Signal Processing and Control. This is a good journal, Q1 rank journal, and I think it's a Q1 rank journal. And Radim was a collaborator. I think these are the three authors of the paper. He's a collaborator. Here, this is the story actually. If you see the database that we had, of course, the database do not belong to us. This database we are taking it from Czech Republic. It's an open access database. Of course, from Brno we got this database. So these are the values of the signals that we had collected, and then we had used. Okay, here I tell you one important thing. I think the one-dimensional CNN model was not pretty much working here. So what we did use the spectrogram method. I do know what's a spectrogram method. Spectrogram method is conversion of the frequency into the frequency component into energy levels. It's a simple. You can say it's a two-dimensional visualization of a one-dimensional signal. And sometimes the discriminatory behavior which is not evident in the one-dimensional a bimetal signal or any one-dimensional signal, it may be visible when you plot it in terms of a frequency distribution two-dimensional graph. So we use a spectrogram. So with the help of this spectrogram, I call it as 1D FHR net. Okay, this word is patented in our name. I mean, we published it for the first time. FHR means the fetal heart rate. So if with this device, with this algorithm that we have published, you can actually make models to take the signal from the pregnant lady, the baby heart sound, and you can tell whether the heart sound is normal or it has got complications of hypoxia, etc. If you are interested with the architecture, you can take a snapshot of it. Here I have given you the complete architecture and the hyperparameters which were most optimized for training the model. Of course, there is not a one-dimensional CNN as I mentioned. It is a two-dimensional CNN because the one-dimensional signal was converted. The time series was converted into a spectrogram model. The results were very good. The results were very good, and we expect to go for clinical trials with the device in KGMU, in King George Medical University in Lucknow. This is how it looks like, that hardware that we have developed. A very easy to use GUI, if you see, and the hardware that we have, very simple, and the device will cost you less than 5,000 rupees, maybe 5 to 10,000 rupees. The entire costing of the device comes out to be. So this is once again a small device. If you can use in primary healthcare centers and villages, you can go for fetal health monitoring system, and that can be a response. It can what you can say, complement in health monitoring of the fetus in primary healthcare centers. I don't know. I'm already 1 hour done. I don't know how much time is left. I mean, am I done with the time? Because I have a lot of slides to show. Do you have some time? Is there
You can continue, no problem.
For 5 minutes? How much time do I have? 10 minutes?
You can take another 15-20 minutes.
Okay, I will finish up in next 15 minutes. Okay, because this is a long slide. Now you see, this is another application of deep learning. When did we publish this paper? Okay, you can see the paper was published in July 2021. Okay, very recently we have published this paper in Biomedical Signal Processing Control. I tell you about this problem once again. Developmental dyslexia, we call this SLI, specific language impairment. You know, this is a disease. Sometimes the children at ages young ages from maybe 2 years to 5 years, they do not develop the language skills, the vocabulary. I mean, they cannot speak properly. Now, to understand if they are, and this dysphagia is a disease actually, which actually is a speech pathology, and we need corrective methods to correct dysphagia. Now here we developed a mobile app. Okay, this was basically this we developed is as a mobile app. It was for commercial purpose otherwise, but then because the science was good, we have published it as a paper. So what we did here is that the sounds of a dysphagia affected children were captured. We made a database. Of course, the database was collected from Europe actually, because European guys, we have some collaborators of European guys also. Radiman, Carlos were the European guys. So we collected a database from dysphagia and we trained them. Okay. Now this is the model you can see. But once again, here what we did is that we did not find enough discriminatory, behavior, and the optimization of the network was not very good when we used the one-dimensional model. So here also, once again, we use a spectrogram-based model. We converted it into time frequency, and the representation of the energies into a time frequency scale was giving you a good discrimination, and the model that we have trained. Because if you really understand one more important thing, I tell you, one-dimensional CNN training is a little bit difficult because you cannot use the pre-existing pre-trained models. I think all of you know that there are a lot of pre-trained models available, like AlexNet and VGG16 and DarkNet. There's so many pre-trained models. So if but unfortunately, if you use one-dimensional CNN model, you cannot take benefit of this pre-trained model is already available. And some of the pre-trained models, for example, the yellow model or the DarkNet or the the VG16 are very popular, and they were lightweight also. They're very lightweight, and it reduces your training complexity. So this is another important thing, that if you can, if it's a one-dimensional, it's a time series, and if you can convert it into spectrogram, of course, the discrimination in the frequency content distribution should be there. So you can go for a deep learning model. So this is the architecture that we had used, the different syllables that we considered, and you can see how the one-dimensional signal was converted into spectrogram because the discriminatory was more. And we used a 10-dimensional cross-fold cross-validation, and mainly you can, if you want, you can take a snapshot of this because the paper is already published, and you can see more about the architecture. But this is now we have it as a mobile app. Okay, we have launched it as a mobile app. You can install it in your mobile phone. Speak if a kid who is expected or who is suspected to be having the dysphagia or the SLI problem, they will speak and then click the mobile button. It will execute the program with that AI model that we have made, and it will tell you whether the symptoms are of SLI, that is, specific language impairment or not. So this is a commercial, a software that we have. But anyway, it has got clinical relevance, and you can always tell it as a biomedical research, and it's published in a paper also. This is interesting actually. Let me tell a moment and tell you. This is also a very recent paper. Did I mention? You can take a snapshot of the paper if you're interested. This paper was published, I think, in 8 June 2021. This is a recent paper. I'll tell you about this paper. This is very interesting. Now, this is about prediction. This is not about, this is a machine learning approach. This is about prediction. Now, for example, if cervical cancer is a huge problem. Many women in our country and across the world are getting affected by cervical cancer, and a lot of deaths are reported, right? So we started working on a prediction model. I think if you're the computer science people, you all know that machine learning works into probability models. So here also we started working with the prediction model. So we got a database, and we collaborated with King George Medical University, okay, and we got a database. I think that we had a database of more than 700 women who were affected with cervical cancer. Then, if you know, in the medical history, normally they will record the socio-demographic characteristics, also the medical parameters. For example, in this particular case, we use cytokine gene variants. These are some genetic informations which you can take from the blood, and also we started relating it with the socio-demographic. I'll tell you about a little bit about socio-demographic habits means your routine life habits and your social and demographic status. I'll tell you. Okay, the study was designed to apply a machine learning algorithm based on some risk factors. And we wanted to understand which are the factors which are increasing the risk of, of getting somebody affected with cervical cancer. Professor Monisha Banerjee is a very nice, quite renowned. She's a dean of Lucknow University. She works with some biotechnology. She was a collaborator and a co-author of the paper. We collaborated through her with KGMU. Now, if you see this, this is the data in which we were working, right? So the risk factor was, let's say, I consider the age below 35 or above 35, the place of residence, labeled it in two terms, like rural and urban. The educational status, if you're literate or illiterate, the socioeconomic status, the parity, then the age at the full term, pregnancy, the menstrual cycle, then the hygiene, the use of constant. If you understand, these are some socio-demographic habits, and this data was recorded for the 700 patients that on which we were conducting this survey. Now we started training a classifier to understand if there is any relevance with the occurrence of cervical cancer with the factors which are socio-demographic in nature, and also the cytokine genetic information. So if you really see, we considered these informations, and we trained some, but of course these were supervised learning because the data was not adequate for deep learning, training deep learning models. We used some supervised learning models, and then we started. Then what we did, we made a model with some risk prediction. Then we brought in unseen data. We brought in unseen data for the test model, the validation and the test model, and we got a very high accuracy. We have given this model to now to KGMU, and they have tested this data to new unseen data. And let me tell you, it is actually giving very high accuracy, more than 90%, that is reported in the paper. But the important thing is that now we know actually what are the factors, the socio-demographic factors or the cytokine gene variant parameters. If you have a combination of these genetic parameters, and if you are having this kind of socio-demographic habits, there is a certain probability of getting cervical cancer with a certain amount of probability. So this paper is already published in Computer Science, Biology and Medicine. You must be knowing it's a Q1 rank journal of the top journals. So if you're interested, you can take a snapshot of this so that you can download the paper and read more about it. This also has a societal relevance, this paper was the work of this paper was also published in some Dainik Jagran and some other newspapers. Why? This makes this brings in some sensitization for the people, for the masses, that this kind of habits, and like smoking, etc. If I have seen, there are some habits. So these kind of habits or menstrual hygiene, if you are not following this kind of if you're following this kind of social demographic habits, there may be a chance for getting affected with cervical cancer. So this was, but if you really see, once again, what I'm trying, you can study more about the the machine learning part of this with the people, but it will give you an indication. If you really see, it will give you an indication how the risk parameters can be calculated, and how the parameters are calculated on the basis of using these trained machine learning models. The summary points are okay. Now this is another interesting application here, but here we used a what we are trying to do here is that we are trying to make a device for visually impaired people. Of course, I need to thank the Department of Science and Technology, because the work is supported by Department of Science and Technology. Here we are trying to make a small device. At real time, this device will visualize the surroundings, identify the objects, and in real time, it will keep telling the visually impaired person in the ear through a small earphone about the object that is available in the surrounding, and also other informations in and around the surrounding, right? But for example, it can tell you about character readings and object identifications. So what did you do? This is the proposed work. I think I don't have much time. We developed an architecture. I'll show you maybe the physical view. So this is the object. This is the device that we have built. the visually impaired person can use this as a as a locket in with a neck hang, and then this device will keep telling you about the devices. So we've trained a model for more than 100 objects. For example, regular objects in routine life that you come across. We use a deep learning model for that. And this is how this is a schematic diagram. If you see, this is the schematic diagram for the visually impaired people. If you can use the device, you will give the carrying of this device. So the backbone of this device is a deep learning model, okay, where we have trained around 100 objects which are commonly occurring. For example, a laptop or a chair or a table. So whatever, maybe a pharmacy symbol or a washroom symbol or a metro station symbol. So these kind of devices, keeping in mind what other maybe the requirement of a visual impact, and we are adding more and more devices. In the first version, we trained it for 100 objects, right? And okay, I thank the Department of Science and Technology. Now, I don't know how much, maybe 5 minutes more. I'll quickly run through them. What we started working with, this is another problem. This problem is about, how we can use artificial intelligence and computer vision to check the quality of fish. Fish is a big staple food in many countries and also in our country also. So Kaushik Banerjee is the director of that Indian Referral Laboratory in Pune and Baramati, and he was the guy who was asking me. So what we did, you can take a snapshot of the paper. This paper was published in Journal of Food Engineering. This is a very high quality journal. It's I think it's more than 5 impact factor journal. So what we did, I'll tell you, we could find 3 tissues in the fish which are discriminatory in nature: the gills, the eyes, and the skin. Now with that, we started working on different problems. Now, whether this fish, what is the freshness content of the fish from the day it was harvested and you bring it to the market, the fish may disintegrate. This is problem number 1. Problem number 2 was the fish exposed to some toxic substance, like for example, cypermethrin. Cypermethrin is a pesticide which is regularly used in Indian paddy fields, in Indian agriculture fields, or it was exposed to some toxic substance like industrial waste, like mercury. Because if you know that a lot of our industrial waste are poured in the rivers, and if the fish is getting exposed to toxic substance like heavy metals like mercury, there is a chance that the fish will be toxic in nature. So we started working on that. Now, if you really see segmentation of the organs like gills, and then extracting the features, and this is another paper you can see. There are many papers that have been published because this was a long-term project we worked. But what I'm trying to only explain, okay, I'll explain it to this figure, this image itself. So the gills, the eyes, and the skin of the fish, if they're subjected to machine learning algorithms and deep learning algorithms, you can see that if the fish which was exposed to heavy metals have shown a discriminatory behavior, so you can build up your AI algorithms. Similarly for the eyes and similarly for the gills. We worked with that. The papers are published. I think I don't have much time. You can take a snapshot if you're interested. This is also a very good quality paper. The results, etc. This is another paper. You can take a snapshot if you want, or you can search. This is another paper which was published. This was a long-term project I did with Biplog, and this was the heavy metal exposure. So here also the same story. We were trying to expose and see, can we feed this data into a network? So this was a biomarker. I think I'm done with the time, right? Or maybe 2 more problems I'll tell you quickly. And okay, let me tell you 2 more problems. I'll take very fast. So this, or maybe some other time. Maybe some other time. I think it's already 5. I don't want you people to keep waiting because I think they're. Anyway, thank you so much. If you have questions, please.
Sir, good afternoon, sir.
Yeah, good afternoon.
Sir, thank you, sir, for your very good presentation, sir, and inspiring too, very much inspiring, sir.
Who are you?
I have some doubts, sir.
Okay.
Sir, you given the intelligent stethoscope and digital stethoscope, sir. Both are same, sir?
No. In digital stethoscope and intelligent, see, one is electronic stethoscope is something where you are putting a microphone and recording. The electronic stethoscope means, you're putting it, recording the signal through an audio jack or a USB cable. That is what you can say. This is an intelligent stethoscope. But sorry, that's an electronic stethoscope. But intelligent stethoscope is something which is integrated with an AI module to take decisions on its own.
Sir, if using this intelligent stethoscope, So is there any drawbacks for patients, sir? I think what are the negatives from the patients?
No, negative means we are, see, this is
Any electro,
I'm not able to understand what you're saying.
so what is there any drawbacks, sir? I'm asking if using this stethoscope
No,
to check the patients.
The drawback means, see, the accuracy may be impacted because you see, the point is, if, see, let us say I have trained my model with 200 samples of mitral regurgitation, right? So, so if, you know, if there is a some sound, some heart sound, which is absolutely not correlated with these all 200, you know, samples that I have trained my model, the accuracy may be impacted. But if you can't say there is any negative thing, these are diagnostic thing. There is no. I mean, these are all positive. I mean, there is. I don't know what to say about negative. If you ask me about the accuracy, I can only tell you that for the 5 cardiac disorders, I had trained it with 200 samples each. Now, if I increase the number of samples in training the version 2 of the model, the accuracy will go higher. Of course, they are augmented in nature, but then if I can train it with more samples, it will go higher. The accuracy will go higher.
Sir, you use it in deep learning models. So how you find the epochs, sir? Epochs values, epochs.
How do you find epochs means for, I don't know, you're asking me how do I decide epoch, or what you're asking me?
Yeah, how you decide epochs in the methodology, sir? You worked in deep learning, COVID-19 many applications.
Okay.
How you find
you're asking me what is the optimized epoch for that model? That is what you're asking me.
epochs, sir? Epochs. You given the parameter.
Okay, I'll tell you. You see, whenever you train a model with a database, and then when you start training, when you start testing it, you'll see after running it through a particular cycle, if you run for 10 epochs or 20 epochs or 30 epochs or 40 epochs, you'll see they start converging, right? At one particular point, both the models, the training model and the testing model, will be closest to each other. That you can say this is the converging model. And beyond that, if you increase the number of epochs, there's a diversion taking place. So that particular point, you know what is early stopping? You know what is early stopping? Are you an AI person? And we consider an early stopping at that stage. Okay, can you hear me?
Yes, sir. Yes, sir. Yes, sir.
So at the point where the training model graph and the testing model graph are closest to each other, you can take that much that value of epoch, and whatever we have reported in the paper, where the minimum, that is the lowest number of epochs in which we got optimized for. If you go for more epochs, there is a chance that you can go for that diversion may happen, and you may have to go for an early stopping. To avoid that, we have already mentioned that. Yes.
Thank you, sir. Thank you very much, sir. Thank you, sir.
I think I should stop.
Thank you. Thank you so much, Professor Datta, for sharing your knowledge in field of artificial intelligence and disruptive innovations. Now I would call Professor Garima Pandey ma'am for vote of thanks.
Thank you very much, sir. Thank you so much for giving me opportunity for saying thank you to Professor M.K. Datta, sir. We are truly humbled by your numerous insightful contributions to this lecture, sir. Contributions of such a great caliber can only come from a true genius person like you, sir. We look forward to having you again in our future events as well, sir. Your presence here definitely enriched this lecture